This is video 26 from digital-university.org, and this video we're going to continue to use the nodal analysis technique, and we want to apply it to this circuit where we have a voltage source and a current source, and then we have three resistors incorporated into the circuit in this kind of a pattern. And again, we want to use our nodal analysis to determine the amount of current going through resistor R1, R2, and R3. Now, with this circuit, there are three nodes to consider. One is down here at the bottom, and it is grounded, and there are two more nodes at the top. This part right here is a node, and over here is another node. And what we've done is we've taken this circuit, same circuit, R2, the current source, the battery, and the other two resistors, and we've just redrawn it like this. So you can see here's the bottom node that is grounded, here's the battery, here's resistor R1 and R3, here's resistor R2 with the current source, and here are the two top nodes. So we'll assign each of these, or designate each one of these a voltage. This would be V1 for this node, and voltage V2 for this node. And then what we'll do is we'll use Kirchhoff's current laws in each one of these nodes here. So that will give us two different equations, and we have two equations and two unknowns to solve for, V1 and V2. So we should be able to handle it. Then once we determine V1 and V2, we can determine the currents through all the respective resistors here in the circuit. So let's go back to here. This is V1. We're assigning that potential V1 and designating this potential as V2. So node 1, node 2, and down here at the bottom is node 3, and node 3 is grounded. Here is node 1 at potential V1, and node 2 at potential V2. So let's consider node 1. And again, like we have been doing in the preceding videos, this is the way they do in a lot of the textbooks. Any unknown currents for this node, when we're setting the problem up, we just assume that the current is flowing away from the node. Here, of course, we know that here for certain we know that there's 2 amps of current flowing away from the node. Now, for the current through this resistor and the current through this resistor, then here at node 1, we're assuming, when we're setting the problem up, that for these unknown currents, that they are flowing away from the node, like this. So the amount of current through this resistor going in this direction would be this potential minus this potential. Both of these are going to be at positive potentials with respect to ground. So if the current is in fact going this way through the resistor, as we're assuming when we set the problem up, then the strength of the current will be V1 minus V2 divided by 4. These are both positive potentials, so this one would tend to make the current go this way. This positive potential would drive it in this direction. We're assuming that the current flow, the net current flow, is away from this node. So that magnitude of that current is V1 minus V2 divided by the magnitude of the resistance, 4 ohms. And same thing now for this resistor right here. The strength of this current is going to be V1 minus 64 divided by 8. And again, we're assuming that these are going away from the node, so they have positive signs. And of course here, there is no doubt, there is 2 amps of current flowing out of the node, and that is set equal to 0. Okay, and again, here the battery with this positive polarity will be pushing a current in this direction. This is at a positive polarity, pushing the current in this direction. And again, when we set the problem up, we're assuming that the net flow of the current is in this direction. So the magnitude of that current would be V1 minus 64. Now, as a matter of reality, the current might be in the opposite direction. And if that's true, once we go through and we determine what V1 and V2 are, we can make whatever adjustments we need to later on. But okay, this is the equation then that we get from node 1. Now, let's go ahead and see what's happening over here at node 2. Okay, at node 2, we notice that there's 2 amps of current going into it here. So here then, that is minus 2. Incoming current is designated with a negative sign. And flowing away from it. Now, for this node, again, all unknown currents, we assume, when we're setting the problem up, are flowing out of the node. So now here, we're assuming the current through this resistor R2 is in that direction, and now the magnitude of it is going to be V2 minus V1 divided by 4. Okay, and now we have this resistor. This is at 0 potential, so the current through this resistor is just going to be V2 divided by 10. So we have these two equations. Now notice when we're setting the problem up, when we're considering node 1, we're assuming that this unknown current flowing through resistor R2 is flowing away from the node, so it'll be going in this direction. When we consider node 2, over here, we're assuming that this unknown current flows away from the node, going in this direction across the resistor. Well, clearly, both of these assumptions can't be right, but again, we'll adjust for that once we determine the numerical values for V1 and V2, and we'll settle that out later then. Okay, so here we have two equations, here and here, and we have two unknowns to solve for, V1 and V2. So two unknowns, two equations to solve for. We should be able, without too much problem, determine what V1 and V2 are. What we're going to do is, right now, just make some more room and then work with these two equations. So let's see, we had V1 minus V2 divided by 4 plus V1 minus 64 divided by 8 plus 2 equals 0. That was from the first node, and then from the second node we had minus 2 plus V2 minus V1 divided by 4 plus V2 divided by 10 equals 0. So let's take a look at this equation, the top equation. Here we have V1 times 1/4 plus 1/8. And here we have minus 1/4 V2. And then from here we have 64 divided by 8 is 8, so minus 8 plus 2 is minus 6. Let's take it to this side, that's plus 6. And then here, so that's from this equation. Now from this equation we have minus 1/4 times V1 and then here we have V2 divided by 4, and we have V2 divided by 10 plus 1/4 plus 1/10. And here we have minus 2, take it over to this side, that equals plus 2. Now 1/4 is 2/8. So here we have 3/8 times V1 minus 1/4 times V2 equals 6. And from this equation we have minus 1/4 times V1, and then from here we have 10 plus 4, we have 14 over 40, or that's 7 over 20, so we have plus 7 divided by 20 times V2 equals 2. So here then are the two node equations, and we can see, yes, we have two unknowns to solve for, voltage V1 and V2, and we have two simultaneous equations. And it's a pretty simple system, but let's just go ahead and set this up and solve it using determinants as you saw us do in the previous videos. And to do that, what we do is, to begin with, here we have the coefficients of V1 in a column like this, and here we have the coefficients of V2 in a column like this. So we're going to have a 2 by 2 matrix with these numbers in one column, and these two numbers in a different column. And we want to first determine what is the numerical value of that matrix. So here we have this times this minus this times this. So 7 times 3 is 21. 20 times 8 is 160. So we have 21 divided by 160. And then here we have minus 1/4 minus 1/4. So we have minus 1 over 16. This is over 160, so if I multiply this bottom part by 10, multiply the top part by 10, and we have this is now equal to 21 minus 10, 11 divided by 160. So we know this. Now, let's determine V1. To determine V1, again, we have these two columns here and here. Actually, we have three columns to think about now. This column of two numbers, this column of two numbers, and this column of two numbers. Now, to determine the value for V1, we replace this column with this column. So we're going to form a different determinant now. There's one column. This column stays the same. And this determinant is divided by the numerical value of this determinant, 11 over 160. So let's see what this gives us. Here we have 6 times 7 over 20. 6 times 7 is 42. So we have 42 divided by 20. And then here we have minus 2/4 or 1/2, and here we have then that's minus this minus 1/2. We have minus 1/2, so that's plus 1/2, and 1/2 was the same thing as 10 over 20. So that's the value for this determinant, and it's divided by 11 over 160. So here we have 52 divided by 20 times the inverse of this, 160 divided by 11. So here we have 160 divided by 20, that is 8. So here we have V1 is equal to 52 times 8 divided by 11, that is 416. Divided by 11, and go to the calculator, that's 37.8, rounded off, 37.81. So we have determined what V1 is. Now, we can easily determine V2, but we're not going to have enough time to do that in this video. Come back, join us in the next video. We'll determine what V2 is, and then we can determine what is the current through these different resistors. Come back, join us for that video, and we'll finish off the rest of the problem.